What I'd like to do now is provide some discussion that will help us understand the lower part of figure 14.1 in Pascal's chapter on where we talk about Pascal's principle. So before I talk about this stuff directly, let me show you a couple of different situations that will give us a better understanding of how to deal with this. So let's imagine that we have a recurved tube. So imagine a glass tube of a uniform diameter that's been curved like this. So it's got a left side and a right side. And I'm going to suggestively just draw a line here for the moment. You'll see why I'm doing that. And let's suppose that in the left-hand side, we initially pour water. So there's water up to this level. And in the right-hand side, we pour another liquid. Let's suppose we pour in liquid mercury. And you'll see what happens here in a moment. But if we have mercury on the right-hand side and water on the left-hand side, we're going to find that the water level on the left side ends up being higher than the mercury level on the right side. So we'll have this height of water. So this is the height above this suggestive line, the height on the left-hand side. And on the right, we'll have this height on the right-hand side. So what is the relationship between the height on the left and the height on the right? Well, let's suppose, I'm just going to use an orange color here to do my calculations. The area on the left-hand side, let's suppose, is equal to the area on the right-hand side. This is because this is a constant diameter tube. Well, if we think of this region of fluid here as being a chamber with two openings at the top, and we have this piston of water pushing down here and a piston of mercury pushing down over here, we know that because those areas are the same, the weights or forces pushing down have to be the same. That is, the weight of the fluid on the left has to be equal to the weight of the fluid on the right. And so this is going to give us a way of understanding what the height of the fluid on the left is compared to the height of the fluid on the right. So what's the weight of the fluid on the left? It's the density of the fluid on the left times the volume of the fluid on the left times G. And on the right, it's the density of the fluid on the right, the volume of the fluid on the right times, once again, G. And you can see right away that G's cancel out. And now what is the volume of the fluid on the left? It's the area on the left times the height on the left. And on the right, density and area on the right and height on the right. And you can see, because the area on the left is equal to the area on the right, I can cancel out these right here. And so we find that density on the left times height on the left is equal to the density on the right times the height on the right. Or in other words, the ratio of the densities is going to give you a way of finding out the ratio of the heights. So for example, if the fluid on the left is water and the fluid on the right is mercury, then the ratio will be 1 to 14 because mercury has a specific gravity of 14. Or we can see right away that on the right, this column will be 1/14 as high as this column. So if this, for example, was 1 inch, this right here would be 14 inches. If this was 2 inches, this would be 28 inches, and so on. Now, let's suppose instead of having a constant diameter tube, we have a tube that has an uneven diameter. This is a little bit more like the case that Pascal is going to talk about. So we have a wide tube on the right and a narrow tube on the left. And once again, let's suppose we fill this with water on the left and we pour a little bit of mercury on the right. I'm going to draw this suggestive line once again. So we're going to have water like this. And on the right-hand side, we have mercury. And the height of the mercury, we'll call that height on the right. And on the left, we'll again call this the height on the left. And let's suppose this is the area on the left and this is the area on the right, but they are no longer equal. In particular, the area on the right is, let's suppose, 4 times the area on the left. It could be any number we wanted to, but let's just use 4 times for the sake of our calculations. Okay, now, once again, we're going to treat this region of fluid below this level to be a fluid-filled chamber with 2 different size openings. And using Pascal's principle, we see that we're going to need to have, because this has 4 times the area, this is going to have 4 times as much weight as this. So in other words, the weight of the fluid on the left is not going to be equal to the weight of the fluid on the right. You're going to have the weight on the right be more. It's going to have to be 4 times as much as the fluid on the left. This follows from Pascal's principle, right? That force 1 over area 1 is force 2 over area 2. So this is just a reminder, okay? Now, let's use this formula. 4 times the weight on the left. What's the weight on the left? It's the density of the fluid on the left, the area of the fluid on the left, the height of the fluid on the left, and g. What's the weight of the fluid on the right? It's the density of the fluid on the right times the area on the right, the height on the right, and g. Let's cancel out our g's as usual. And then 4 times the density of the fluid on the left, area on the left, height on the left, and on the right, density of the fluid on the right. The area on the right we've said is 4 times the area of the fluid on the left, like this. So I plugged in 4Al for AR. Now notice what happens. The 4's cancel out, AL's cancel out, and we're left with density on the left times height on the left equals density on the right, times height on the right. Notice that this is the exact same formula. In other words, density left over density right equals height right over height left. These are the same formulas. In other words, the ratio of the heights, it doesn't matter whether this is a tube of a constant diameter or a tube of an unconstant diameter. You're going to have the same ratio of the fluids on the right and on the left. And again, this follows from Pascal's principle. So if the fluid on the right had a density 14 times the fluid on the left, like mercury compared to water, then once again, we're going to have that. So this is the case of mercury. So why are we talking about this? Well, because that helps us understand what's going on in these diagrams. So I want to just end my discussion by talking about some of these diagrams. What he's showing right here is, imagine that we have a lake of water, and if we have a recurved tube filled with mercury, you might imagine, that all this fluid above right here is a column of water weighing down on this opening, and it's pushing the mercury up in this direction. This tube is full of air. There's no water in the tube. So this, if we were to draw a line across right here, that would be a bit like drawing a line across right here. But in this case, it's purely mercury like that. And here we have, let's suppose we had 14 feet of water weighing down. Then we would have 1 foot of mercury right here above this level, because 1 foot of mercury balances 14 feet of water. That's what he's demonstrating right here. It doesn't matter whether it's curved or not. We could have a tube right here, and we have some mercury in the bottom. If it's open at the bottom, all this water right here, let's suppose that the bottom right here is 14 feet below the water. So you have basically 14 feet of water that's pushing down, and it's pushing up on the bottom there, and it's holding up 1 foot of mercury in there. So what he's showing here is that 14 feet of water holds up 1 foot of mercury. If you were to pull this tube out a bit, so the bottom was, let's say, at 7 feet, then you'd have 7 feet of water, and it would be holding up a half of a foot or 6 inches of mercury inside of the tube. So there's sort of the water and the mercury are balancing each other, but the ratio has to be 1 to 14, provided that's mercury and water. What he's showing in Roman numeral 11 is that if you have a recurved tube, I'm sorry, not a recurved tube, but a tube like this that's only has air in it and it's open at the top, and you put a wooden cylinder in the bottom that's free to slide up and down, well, what's going to happen is all the water over here is pushing down, and it's pushing up on the bottom of this wooden plug, and it's pushing it up into the tube. So that weight of the water is shoving this wooden block up into that tube, so it's going to hold it up in. And it doesn't matter whether it's a straight tube or a curved tube. If this is air inside of the tube, you can have all this water right here weighing down and pushing this wooden block that would ordinarily float, but it's pushing down on the top and trying to push it into the tube like that. So you might want to take a little bit of time going through some of the text and reading how Pascal explains these situations. Those are described on page 183, 184, 185, around there. So take a look at those, and next time we get together, I guess electronically, we'll go on and talk about chapter 15. See you then.